Okay, so what you're about to see is the end of 10.3. 10.3 is where we started studying polar coordinates. So now we're going to introduce a little calculus here. So look at what this one says. It says, in the example, find the slope of the tangent line to the function is r equals 2 sine of theta. And we want to find the slope of the tangent line at theta equals pi 6. And you might think we have to learn something new since we're in polar coordinates, but we don't, because we can use what we know about finding the derivative parametrically in terms of a parameter. In this case, the parameter is going to be theta. And here's how we can do that. We can use the transformation equations. We can use the fact that x is equal to r cosine theta, and y is equal to r sine theta. And we talked about those equations last time. And what we have to do, though, is get a single parameter. And the way to do that is to plug in what r equals, our function r equals in terms of theta. And we do that, we plug that in, that 2 sine theta right there. And then we also plug it in right there. And that gives us our parametric equations. In fact, when I first started studying math back in the Stone Age, they didn't, the TI-81 calculator didn't have a polar mode. What you did was you went in parametric mode and plugged them in like I'm about to show you. So if we do that, our parametric equations become x equals, okay, plug in right here 2 sine of theta. So 2 sine theta cosine theta, right? R cosine theta, R is, at least on our graph that we're looking at, R is 2 sine of theta. So plug that in for R. And then y is equal to, okay, plug in 2 sine of theta right there. So that's 2 sine of theta times sine of theta. So we'll definitely simplify that in a second. I just want to pause for a second. That's it. Those are our parametric equations. If you graph those equations in parametric mode in your calculator, it's the same thing as going to polar mode and graphing that, which will turn out to be a circle. But we do want to simplify it. I think it'll come in handy to use a trig identity on 2 sine theta cosine theta. Does anybody remember what that is?
Double angle.
Double angle. So which one?
It's 2 sine theta, right?
Close.
Or,
sine of 2
no.
theta. Sine of 2 theta.
Oh,
Remember,
that's what I meant to
sine
say.
of 2 theta equals 2 sine theta cosine, yeah. And then I'm just going to rewrite the y as, oh, it's 2 sine theta, 2 sine squared theta. So those are our parametric equations. Now think about what we want to do. We want to find the slope of the tangent line. Oh, what gives us the slope of the tangent line? What is the slope of the tangent line? You guys know this. I know you know it. You're just being shy. So if you have a curve, this guy happens to be a circle. This happens to be a circle. I'll show it to you on the calculator in a little bit. And we're just trying to find the slope of a tangent line at theta equals pi over 6. I think as it turns out, that tangent line would be over here somewhere. I'll show you in a little bit. But what idea from calculus, really calculus 1, the derivative, yeah. So if we could do it, we would just take dy dx as our slope. But we have to do it parametrically. So you guys know from what we studied earlier in 10.2 that dy dx, if the parameter is theta now, is dy d theta, not t, because the parameter is called theta, not t. That's the only difference here. Over dx d theta. It's the same formula as from 10.2 for the parametric derivative form. So, so that means we find these derivatives and then we evaluate, or we find these individual derivatives and take the ratio, and that'll be dy dx in terms of theta. And then we plug in theta equals pi over 6 to get an actual slope. Okay, so let me go up here to finish it off. What is dy d theta? So you're going to want to go to the simplest version of y in terms of theta, which is this guy. So that's going to be our numerator if you take the derivative of that. So what's the derivative of 2 sine squared theta? I know you know this. Use the force. So 2 sine squared theta is really 2 sine theta, the whole thing squared. So what rule are you going to use?
Chain rule?
Eventually, yeah, but at first, what are you going to use? What are you going to do with that power?
Power rule.
Bring it down in front. Okay, so that gives us 2, well, let's just call it 4, how about, right? 2 times 2 is 4, instead of going 2 times 2. So how about 4, okay, sine of theta to the 1 power, right? You subtract 1 from that exponent, but then what do you have to multiply by? Oh, and I kind of had the parenthesis in the wrong place here. So that 2 on the outside is not getting squared. But anyway, you bring that 2 down, you get 2 times 2 is 4. The new exponent is 1, but then by chain rule, you have to multiply by the derivative of what's inside, which is cosine theta. And I know you guys are rusty because you've been working more with integrals this semester than derivatives, but does that ring a bell?
Yeah.
It comes back quickly. Yep. And then, so that's the derivative of y with respect to theta. This guy, what's the derivative of x with respect to theta? So now you got to focus on that version of x. So what's that going to be?
Cosine 2 theta.
Cosine 2 theta.
Times 2.
There you go. There you go. So yeah, cosine 2 theta times the derivative of the inner function. The inner function this time is 2 theta, so times 2. Does everybody buy that? Okay. So what could I do then? Okay, first of all, I could take the 2 into the 4 and get 2. And then what's on top? How could I simplify 2 times sine theta cosine theta? What does that turn out to be?
Sine 2 theta.
So it's just sine of 2 theta, I think I heard. On top, right? Cosine of 2 theta on the bottom. And how does that simplify? Or I think you could call it simplifying. What could you replace sine over cosine with?
Tangent.
Tangent.
There you go. So tangent of 2 theta. Parentheses are optional around the 2 theta. Okay, so we're not done. We're almost done. But any questions at this point? Okay, so remember what we want to do. We want the actual slope of the tangent line at theta equals pi over 6. So here's a way to denote that. dy d theta evaluated at theta equals pi 6. That's a way to denote that. And so if you do that, if you plug in pi over 6, you actually get tangent of pi thirds, don't you? 2 times pi 6. And that's tangent of 60 degrees. Turns out to be rad 3 is our slope that we're looking for. Any questions on that? So on the calculator then, it's always fun to play with the calculator. So let's do this. I really encourage you to use the technology to kind of check your answers and make sure they make sense. So let me, hold on. Let me switch the share. Okay, so you should see my calculator now. Let me know if you don't. And then let me go ahead and switch to polar mode. I'm in parametric mode from the other day. So polar mode. No, I'm sorry. I do want, nah, it doesn't matter. I'll do it in polar. I could do it parametrically. but it's easier in polar. So let's go to y equals. Try again, y equals. And let's type in the original 2 sine of theta. So 2 sine theta. And then let's just graph that. Zoom number 6. Let's zoom in. Go to zoom, zoom in, press enter. And then if you go to zoom square, it'll look more circular. So zoom number 5. There you go. So what we're saying then is, let me see if I can put this picture in OneNote somewhere. So I'll put it right there. Okay, so, whoop, a little bit large. Okay, so that's a picture of the curve we're interested in. So if you think about it, the equation of this curve is r equals, what was it, 2 sine theta. And it is traced out as theta runs from 0 to either pi or 2 pi. That's usually the boundaries. I think it's going to be pi, and you can check it real quick. So even though we graphed it on the calculator, let's check it by hand just to give us an idea of how this thing is traced out. So r theta. Look, if I plug in 0, for sine, I get 0 popping out, don't I? So then you're right here at the pole. If you use polar coordinate language, you're at the pole. When r equals 0, you're at the pole, which is, it corresponds to 0, 0 in Cartesian coordinates. And then if I plug in like pi over 2 in here for theta, that, oh, sine of pi over 2 is 1, I get 2. Oh, so I've gone all, you could check some points in between if you want, but I've gone all the way over to here. And then if I plug in pi, sine of pi is 0, I'm back to 0. So this thing is traced out over just 0. Theta goes from 0 to pi. So where would it be at pi over 6? Well, to give you an idea, you could just plot the point by hand or hit trace on your calculator. If you hit trace on your calculator and then plug in pi divided by 6, hopefully I'm in radian mode, pi divided by 6, I should be. So you're right here, and then the tangent line would be right there. And so what we found was the slope of that tangent line. So it's somewhere, so I'm not too far off. Let's see, it'd be somewhere around here. Let me use a different color. Somewhere around here. We're saying the slope of that tangent line is radical 3, 1.7 maybe. So just to give you some bearings to give you an idea of what we just found. So the slope of that line is radical 3. If this is the point you get when you plug in theta equals pi thirds. So the R value is whatever it is. I didn't find it, but hopefully that picture will give you an idea of what the heck it is we just did. Any questions on that?
Professor, I have a question.
Uh-huh.
For the dy over d theta, is that supposed to be dy dx?
Yes, thank you for pointing that out.
Thank you.
Dy dx. I mean, it's supposed to be the same thing as what I said right here, right? And that's just my left hand not cooperating again. I don't know why it does that. Okay. Dy dx is what we found with respect to theta, right? In terms of theta. Any other questions? Okay. So couple of notes here. I can get this stuff out of my way. Hold on. Okay, couple of notes here. Number one, to find an H tangent, that means horizontal tangent, to a polar curve, just like before, you're going to set the numerator of the derivative. Remember, the derivative dy dx is equal to dy d theta, if you want to put the derivative in terms of theta, over dx d theta. So what do you do to find a horizontal tangent? You set the numerator of that derivative in terms of theta. You set that numerator equal to 0. Same as before. Nothing's changed, you guys. Same as in 10.2. We just called it dy dt in 10.2. And then to find a vertical tangent, remember, you set the denominator equal to 0. That's what I'm saying right here. Same as in 10.2. Now, be careful. If dy d theta and dx d theta both equal 0, then the determinant is 0 over 0, right? And you've got an indeterminate form for your derivative, rather. Sorry, I misspoke. Now, what that means in practice is you're not sure if you have a vertical tangent where you get 0 over 0 for the derivative or a horizontal tangent. Okay. Well, what kind of curves will you have to worry about that with? Well, it'll be like, remember the cardioids? So they look something like, perhaps like this. Or maybe, and it's very symmetric, so it's a little bit off on this side, a little too high over there. But cardioids have a cusp, don't they? And the way I've drawn this one, it'll have a vertical tangent at that cusp. And it looks like it should have a vertical tangent there. Or if it were upside down, it would have a vertical tangent there. But you've also seen cardioids that where the cusp kind of is oriented like this, right? Again, another terrible picture. I can do better. No, I can't. So if you get one oriented this way, another terrible picture, then hopefully what I'm trying to get at is you'll have a horizontal tangent. And that's kind of an informal way of determining whether or not you have a vertical tangent or a horizontal tangent, because I believe, if I remember correctly, in both these cases, you'll get a 0 over 0 situation. And that's as far as we'll take that this semester. There's ways you could do it more formally with one-sided limits, but we're not going to go there. So that's it for this section. Just beware of cardioids when you're looking for horizontal tangents or vertical tangents. You can pretty much graph them to verify whether or not you have a horizontal or vertical tangent, is what I'm telling you. Any questions on, this was 10.3 we just finished up. There it all is. Did you get all that? Oh, well, if not, read through the notes. Any questions? Okay. Well, we do need to get started on 10.4 tonight. So let's do that right now. Give me just a second to get to the right file. Okay, here we go. So we're talking in 10.4, we're talking areas and lengths in polar coordinates. The goal is to evaluate area integrals in polar form and to find lengths of polar curves. So let's get started on that. Here we go. I have to remind you of a couple of things in order to do that. So focus your eyes on this circle right here. I don't think I need to tell you that this distance from here to here would be a radius of the circle. We usually call that r, generically speaking. And then if you're carving out kind of a piece of pie, I guess we could call it, it's a circular sector, then theta would be the angle, the smaller angle of the tip of the pie. So theta is this angle right here. And then the crust of the pie, we usually call S. So that's an S right there, not a 5, but an S. The crust of the pie has length S. And you may remember from pre-calculus then that S is equal to R times theta. So I needed to remind you of that formula. And then here's a formula you probably didn't see in trig or pre-calculus, or if you did, you probably don't remember it. The area of a circular sector, so the area, A for area of a circular sector, so I'm talking the area of this piece of pie. Pie. How did I forget to say that? The area of that piece of pie is actually 1/2 r squared times theta. And that's, if you're anything like me, that formula would be less familiar to you. So how do you verify that formula? One way you could do it is you could think about the ratio of arc length. So like S. So, but I'm going to write it out. Arc length, you could think about this ratio. Arc length to the area associated with that arc length. So the area associated with this arc length of S is the pi, if that makes sense. And then the way you could come up with that formula is you could create a proportion. So the proportion you could create is, if you think about the arc length all the way around the circle, that's the circumference, and that would be 2 pi r. And you could put that in ratio to the area of the circle, pi r squared. You know these formulas. That's why I'm grabbing a hold of them. And so what we're saying is with any circle then, the arc length in ratio to the associated area of the piece of pie, in other words, length of crust to the area of the piece of pie on top, is going to be equal. So this ratio should equal S to the area of the piece of pie. So I'm using very technical math language here if you can't tell. So that's the piece of pie. And then if you realize that S is R times theta, so let's replace S with R times theta, then solve, I'll let you guys do it, but if you solve this equation, you cancel out a couple R's here, cancel out a pi. If you solve that equation for area, so solve for that guy, you're gonna very quickly get 1/2 r squared theta. And that's where the formula comes from. So we need both of these results to understand the integration formula I'm about to present to you. Okay, any questions on that? Okay, so let's get to it then. So I drew a wonderful picture for you ahead of time. So what we're imagining here is this curve in red is a polar curve. So in other words, it can be described by an equation R in terms of theta. R equals f of theta, okay? So that curve in red is given by the graph of R equals f of theta. So consider R equals f of theta. Now, it has to be true in order for the formula I'm about to present to you. It has to be true that this f is continuous and smooth, which means you're not going to see any cusps anywhere in this curve. And it's on the interval from A to B, where A and B are angles this time. And the difference between them is bigger than 0. So A is bigger than B, but less than 2 pi. So we're not going around doing a 360 here. We're not going around more than once. Then here's the idea. Remember what I'm trying to do. I'm trying to develop an integral that'll give us the area here. Okay? that's not quite a piece of pie because that curve in red's not quite a crust. But that's the analogy we're building, and we'll be able to come up with an integral that gives us the area of that region, okay? So what we're trying to do is we're trying to find the area of this region in here, okay? Call it R for lack of a better thing to call it. Okay, so what I'm doing then is I'm saying, hey, A is an angle, so this is angle A right here. And I'm saying, hey, B is an angle, so this is angle B right here. But I'm going to erase those because they get in the way. And what I'm going to do is I'm going to partition this. Well, it's not a piece of pie. It's almost a piece of pie. But I'm going to partition this guy in an analogous way to how I partition like the area in Calc 1. And as you've seen me do a little bit in this class, like I would partition the area between the x-axis and a curve, given y as a function of x. I'm going to do it in much the same way, but you have to remember, we have to think radially and angularly when we're in polar coordinates. So the way I partition this almost piece of pie is I break it up into a bunch of smaller pieces that are almost pieces of pie. And in fact, maybe even closer to looking like pieces of pie than that big region. So I'm only going to do a few subsectors, almost sectors here. But the idea is, okay, this angle here then would be theta 1, A would be theta 0. And then this angle, so this would be theta 1. This angle here would be theta 2 in this partition I'm creating. I'm creating a partition and subintervals. This angle here would be theta 3, but I'm going to erase all that stuff because it's going to make a mess. And then, actually, let me erase that and then keep theta 0 right here. And then B would actually be theta n, the end of the n subintervals. Okay. So again, this is going to be analogous to how we created the integral in rectangular coordinates. So what I want then is I want an estimate of the area of, let's say, the ith almost sector. So let's pretend like this isn't the second sector. Let's pretend like it's the ith sector. So we want A sub I, the area of the ith sector. And I'll put sector in quotes because it's not quite a circular sector, is it? Even though the smaller the smaller you make your sub theta values, in other words, the more partitions you make, the closer this will be to like the crust on a pie, circular. That's the idea. As long as you have a nice smooth curve. So A sub I is going to stand for the area of the ith sector indicated in purple there. And then using that formula above, okay, which formula am I talking about? I'm talking about this formula. We can come up with an estimate for the area of that ith sector. So the area of that ith sector, well, it's going to, since it's not truly a circular sector, it's going to be approximately obtained using that formula above. But think about what we have to do. It's going to be 1/2 r squared. In this case, theta would be, let's see if it shows up. It would be this, it doesn't show up, hold on. So theta would actually have to be called this angle right here. And we actually would call it like delta theta. And the delta thetas don't have to be the same in all the subintervals, but they could be. So you could call it delta theta sub I if they're not all the same. So we'll put on a delta theta instead of theta on the end, but it's still a theta, it's still an angle value. So we're still just using the formula 1/2 r squared theta for the area of a circular sector. What we're saying is this A sub I is going to be approximately equal to that. But remember what R is given by. R is given by the function. So this would actually be 1/2, okay, f of, well, okay, whatever your sample theta value is, we could call it theta sub I. And then delta theta, or delta theta sub I. So that's an estimate of the area of the ith sector, almost sector. Okay? And then think about what we're going to do if we want to get an estimate of the total area of this region. We're going to add all such a sub I together, aren't we? Just, in other words, we're going to create a Riemann sum, aren't we?
Professor,
Uh-huh.
do you have to square?
And we have to square this, yes. Okay. So what's the total area going to be? It's going to be the sum. Okay, think about what we've done in the past. I equals 1. We've split it up intentionally into n actually, sub intervals angle-wise. So the sum from I equals 1 to n, 1/2 f of theta sub I squared. And when I do this, if it helps, you could put in outer brackets to say, oh, I'm squaring the entire f of theta sub I. But you don't have to have those there. Delta theta. And then the idea is to take the limit of, okay, it's a Riemann sum. Take the limit as n goes to infinity. Take n to infinity. If that limit exists, we call that an integral. And we use this symbolism, which shouldn't surprise you. The integral from a to b, 1/2 f of theta squared d theta, or what I think is a friendlier looking formula, the integral from a to b, 1/2 r squared d theta. Remember, f of theta is r. So I just replaced it with r. So long story short, that's the formula we're going to be using to find the area of a polar region. So this gives us the area of a polar region. Does that make sense to you guys? Shouldn't be, you might not have understood every detail there, but shouldn't be too far-fetched, right? I mean, based on what you've done in the past with rectangular coordinates. Okay, so let's see how we can use this. We're going to go ahead and find the area of one petal of the rose curve, r equals 3 cosine 3 times theta. Okay, so you can use technology to help you graph these things. I usually show you how to do it without technology. I don't have to graph the whole rose curve. In fact, using symmetry, all I really need is half of a petal. And I can multiply by 2 the area I end up with to get the full area. So it is a good idea to graph at least part of it, though. So let's do that. I don't have polar graph paper, so I'll go ahead and use an XY plane. Think about what I want to do here. I want to graph r and theta, right? And usually what we do for rose curves, for limacons, we start theta at 0. And so if you think about it, if you start theta at 0, 3 times 0 is 0, you get the cosine of 0, which is 1 times 3, which is 3. And so we get, now, okay, you have to look in the direction of 0 and go out 3. That's how you think about it when you're graphing in polar coordinates. Look in the direction of the angle and then go out the radius, which is 3. Or the r value if you don't want to call it a radius. Okay. So now, look. I know from experience the way these things are carved out. First of all, I know the number of petals when n is odd. N is the number of petals when n is odd. So n equals 3, you get 3 petals. And you could check this on the calculator, but I happen to know how this thing is traced out as theta increases. It's going to be traced out like, I'm going to erase this. I'm not going to draw the whole thing. But it's going to be traced out something like this. Oh, that's terrible. So I'm going to erase that last part of it. Now, how am I going to get back to the pole? Well, if you think about it, what theta value is going to bring me back to the pole for that first part that I traced out? Remember, I said it goes like this. What theta value is going to bring me back to that pole? Well, it's got to be when the angle that you take the cosine of becomes 90 degrees or pi halves, right? So when does 3 theta equal, that's supposed to be pi halves, I was thinking ahead. When does 3 theta equal pi halves? Well, divide both sides by 3 or multiply by 1/3, and you'll get pi 6. So in other words, if you plug in pi 6 in here for theta, you end up taking 3 times pi 6, that's pi halves. Cosine of pi halves is 0, times 3 is a radius of 0, r equals 0. So what I'm saying then is you're going to carve out or trace out half of one petal if you let theta range from 0 to pi 6. That's all I need to set up my integral. I'll show you why in a second, but you guys see how I got that? And again, if you don't believe that, you could either do this. You could plot a theta value in between 0 and pi over 6. Or you could just plot it on the calculator and see that, yeah, it traces it out that way as theta increases. The calculator will trace it out the way I showed you as theta increases from 0 to pi 6. So we've got half of one petal, and it's going to be symmetric with the other half. So the idea is that the area contained here will be half the area of the complete petal. The other half would be down here. So what I'll do is I'll set up the integral to find that area that I indicated, and then just double it. So let's do that. So, I recommend writing the formula down. I usually pull the 1/2 to the outside and make it 1/2 integral a to b r squared d theta. Okay, so what the heck is r? Well, it's pretty much given to you. R is going to be given by 3 cosine 3 theta. Now, I want to make a point here, though. I want to make a point as to how to informally think of this symbolism here. And it will help you set up the integral. And it's going to be analogous to using, remember when we used vertical and horizontal rectangles to help us set up area integrals way back in chapter 6? It's going to be analogous to that. So I need to zoom in on this thing. Let me go 250% and see what we see. So it wouldn't be a bad idea to get in the habit of drawing not a representative rectangle, but a representative sector or almost sector, if you like in the picture I drew above. So here, what you want to do, I mean, you don't even need to draw a sector once you get used to it, but what you need to do then is from, in this case, the origin, draw a line kind of just in a random direction that'll hit the curve. And then if you think about it, so I'm going to draw in like a representative sector here. And I won't normally draw this. Normally I'll just draw it as a radius. But I want to make the point here that remember what we did to create the integral. The idea was, we'd find the area of the AI, the ith representative almost sector. And that's kind of what this picture represents. Instead of a vertical or horizontal rectangle, you're drawing an almost sector. And it reminds you what the integral stands for. What does the integral stand for? Okay, back to the original zoom. Well, if you look at just this part, including the 1/2, so maybe for explanation purposes, maybe I'll leave the 1/2 in there right now. If you look at just this part, then you can kind of think of this as the area, the 1/2 r squared d theta of an infinitesimally small, I'll just say really small, it's easier to spell, really, really small sector, almost sector. I'll call it a representative sector. Almost, representative almost sector would be better to put that first. Instead of a representative rectangle. I'm not spelling well tonight. Okay, representative. It's a representative almost rectangle. That's what this guy represents. And that's what I drew in the picture. And that won't help you so much now, just like when we first looked at areas between curves, the purpose of that representative rectangle really helped you out later on when you were finding like volumes of rotated solids. But being able to do this will help you out, if not this semester, later on, drawing this representative polar sector. Okay, so that's what that represents, and it tells you, oh, you got to go all the way from the pole to R. And what function R of theta gives you that, or what function R in terms of theta rather gives you that curve in orange? Well, it's this one. Okay, now in practice, it's not going to take that long to do this, especially a problem as easy as this one. What you're going to do is just fill this in. Now, remember, we want to double the area. So this is a generic formula for area, but the particular area we're looking at, that's just half of one petal of a rose curve. So we want to double this. We'll take the 2, bring the 1/2 out front, integral from, that was the purpose of this over here. To trace out half of one petal, you got to go from theta equals 0 to theta equals pi over 6. Those are your limits of integration. And then you have to square R in terms of theta. So you got to put parentheses around it, square the whole thing, d theta. Any questions on that setup? I think I'm going to evaluate this one. I'm not going to evaluate many integrals tonight because they take a while, a lot of them. But I do want to at least evaluate a couple of them for you. So I think we'll go ahead and evaluate this one, and then maybe we'll take our break. So first of all, let's simplify, of course. We'll bring a 9 out front, because remember, you have to square the 3 and the cosine of 3 theta. So let's square that 3 and bring it out front. Make it 9. 9 times the integral from 0 to pi 6 of cosine squared 3 theta d theta. Does anybody remember how to handle this? By the way, this is a good review for the final, guys. Good review of chapter 7 stuff as far as techniques of integration. So talk to me. How do I handle that, an integral of a cosine or sine squared? Either one, you do it in a very similar way.
Is that the power reducing?
Good old power reducing formula. So, okay, let's think about this. If it's just the cosine of, I'll use x since we're using theta already. If it's just the cosine squared x, do you remember what the identity says? It becomes 1
Plus cosine 2x over 2.
Cosine 2 times the angle, right? Over 2. In fact, you can derive this from one of the double angle formulas for cosine. You can derive this formula. So that means you double whatever is right here and put it right here. Oh, and I'm going to pull this division by 2 out front to write it as 9/2 integral 0 to pi 6. And then the 1 plus cosine of 2x actually becomes what? 1, since it's really 3 theta that we're dealing with, not just x, but 3 theta. 1 plus...
cosine 6 theta?
You got it. 1 plus cosine 6 theta. Yep. D theta. And then any questions on that? Okay. So help me out here. Let's integrate. We get 9/2. I'll integrate 1 for you with respect to theta. I'm that nice of a guy. It's theta. Yeah, that was hard, but I did it. You know, I got through it.
Professor,
Yeah.
where did you get the 9/2? Am I missing that, or did you?
Okay, in the identity there, in this part of it, that division by 2 would be right here, but I went ahead and brought it out
Gotcha.
front.
Okay.
Does that make sense? Okay. So now integrate for me cosine 6 theta. See if you remember how to do that. Obviously, it'll involve sine, right?
1/6 sine 6 theta.
Good, Jonathan. Yeah. 1/6 sine of 6 theta. And then we're evaluating from 0 to pi 6. Don't forget that. Everybody believe that? Let's see if I can squeeze the remaining right here. I try to keep everything on one screen for you so I don't scroll too much. Okay, so let's go ahead and plug in the pi over 6 in for theta. So fundamental theorem of calculus. Now, pi over 6, and then what are we going to get for 1/6 sine of 6 times pi over 6? Well, you get sine of pi eventually, right?
That should just be 0.
Just 0, yeah. Minus, what happens when you plug 0 into both of these? Not a lot, right? 0. So we get 9 pi over 12, but what does that reduce to?
Three-fourths pi.
There you go. And that's, if you had units, it would be in square units. You don't have to write down square units, but if you are doing an applied problem, you do have to write it down, whatever the units happen to be. There it all is. That's what you're up against. Any questions?
I have a question. When you first started off your A for your integral, why is there a 2 times 1/2? I didn't understand the 2.
Because if we didn't have this 2 right here, all we would have found is the area of this half a pedal. But we wanted to find the area of the entire pedal.
Oh, okay.
Okay, so I doubled it. I just used symmetry.
Okay.
Yep. Any other questions? Okay, that's a good place for a break. So let's take 10, and then we'll come back and wrap up this section. This one, you can see I worked it out for you because it was quite a bit of work, and I'll show you that when we get to it. So in this problem, we're going to go ahead and find the area of the region that lies inside r equals 1 minus sine of theta and outside r equals 1. It is pretty critical that you can graph these things. Again, you can use your calculator as an aid, but I'll show you how to do it by hand in case you have something against calculators. I don't know why you would, but just in case. So let's start with the cardioid. If I wanted to graph the cardioid, how do I know this is a cardioid? Well, it's of that form r equals a, either in this case, the minus part of the plus or minus sine of, well, b times sine of theta. It's in that form. And in fact, when you have the absolute value of a over b, which is 1, well, a over b is 1 over -1, and then you take the absolute value of it, you get 1. I know when that happens, you have a cardioid. I suppose these days you don't have to have that memorized because, well, you have a calculator to show you that. So it's one of those ones with a cusp as opposed to an inner loop. So anyway, r theta, I don't have to have a great picture here. So I'm just going to plot 0 for theta, pi halves. I'm going to plot pi, 3 pi over 2. And then if you go all the way around, you'll have the same r value as if you plug in 0, if you plug in 2 pi. Okay, so if you plug in 0, you guys know that the sine of 0 is 0, so you must have an r value of 1 if you plug in 0. And then if you plug in pi over 2, the sine of pi over 2, 1 is 1, 1 minus 1 is 0. So r goes to 0. You're at the pole. Doesn't matter what theta is. If r equals 0, that point is essentially at the origin, if r equals 0. If you plug in pi for theta, that's sine of pi is 0, so you get 1 for r. 3 pi over 2, the sine of 3 pi over 2 is negative 1, and then you'd be subtracting a negative 1 from 1, so that would be actually be 2, wouldn't it? And then you'd be back to an r value. If you plug in 2 pi, you'd be back to an r value of 1. So it's because we know so much about this graph going in that I can graph it pretty quickly and say with confidence that, okay, if that's 1, negative 1, and that's 1, just thinking Cartesian wise, really. But if we want to think 1, 0 as a polar point, you look in the direction of 0 radians, and then you go out a distance of 1. So that puts you right here. And then if you look straight up at pi over 2 is up here, from the origin, that is, you go out a distance of 0, so you're at the pole. If you look to the left in the direction of pi from the origin, you're out a distance of 1. And if you look in the direction of 3 pi over 2, which is straight down, you're at a distance of 2 in that direction. So 3 pi over, so that's 3 pi over 2 direction-wise, straight down, you're there. And so I know it's going to be a cusp right here at the origin. And so just from the points I plotted, I'm pretty sure, I don't know how high exactly it goes in the second quadrant here, but I'm pretty sure it'll look more or less like this. And try and make it look symmetric with the, essentially the y-axis, theta equals pi over 2. Not too bad. I've drawn worse. And so that's our cardioid. R equals 1 minus sine of theta. And of course, yes, check it on the calculator. By all means, do that. When you're doing the homework or the test, it's nice just to have that little security blanket with you. And then r equals 1. What does that graph to be, you guys?
Circle radius 1.
Centered at the origin, yeah.
Yep.
Yeah. That's actually kind of hard to draw, freehand anyway. So let me go up a distance of 1 here, and then our circle, more or less, it would look like this. And then now we can think about what it's telling us here. Find the area of the region that lies inside the cardioid, outside the circle. Oh, does everybody see what that is? That would be like this. I don't want to color it all in like that, but it would be that area in there, wouldn't it? So I'll just shade it a little bit. Looks like it has teeth now. Does everybody understand what area it is we're trying to find here? Okay. So, you know, there's a couple of different ways to go about this. And when you get to Calc 3, there'll actually be a way that's a little slicker than what we're doing here. But really, I think if we just thought in terms of maybe the semicircle for r equals 1 that lies below the x-axis of that area, that's an easy area to find, isn't it? And then what could I do with that area? We're not actually looking for that area, but I can do something with it so that I could find the whole area. So if somehow I knew the area of the cardioid that lay below the pole, the polar axis, we'll just say the x-axis, because that's actually includes the negative x-axis. So if we somehow knew the area of the region created by the cardioid of, I'll just say cardioid region below the x-axis, if we somehow knew all of that, so that's more than what we're looking for, right? That's like including this part too. What could we do though with that area of the semicircle?
Subtract it from the area of the cardioid.
Yeah, so we could subtract the area. It's really the area of the circle below the x-axis, but it's the area of the semicircle, half the circle, area of semicircle. And that would be a way to think about it, a good way to think about it. So what I'm trying to say is this, then, in words, would be the area that we're trying to find. So I could just say that is equal to the area A that we're looking for. Okay, so that simplifies things because I know how to find the area of a semicircle. That's not going to be an issue because I know how to find the area of a circle. So I know how to find half the area. So I need to find the area of the cardioid region that the region bounded by the cardioid that lies below the x-axis. So if you think about it, to get to this point right here, if you think about how this thing is traced out, so the cardioid, you could graph it if you wanted to, but you can kind of see it from the theta values increasing over here, what kind of R values we got. You can see how this thing is traced out. It's traced out starting here if theta equals 0, and it's traced out in this direction. When does it go below the x-axis? Not until theta is
Pi.
Let's
Over
see.
2.
No, at pi, right? Because that's
Pi.
that's the value of theta that gave us this radius of 1. That's the value of theta that gave us this point, right? So after it gets to pi, then the R values dip down here, right? And they point in this direction, really, below the x-axis, don't they? And so then then we get back to this point as theta goes from pi to 2 pi. So that's how you can get your limits of integration. Does that make sense? And if you want to draw your polar sector, just to be consistent with the way I showed you before, it would be, okay, remember we're finding the whole area right now. And your polar sector or almost sector would go from the origin or from the pole to the curve. You could just draw a radius or kind of make it look like a almost sector if you wanted to. And so, oh yeah, so what this integral, so the generic integral, remember, is a to b 1/2 r squared d theta. What this part of the integral represents after the integral symbolism is the area of this, supposedly super tiny, almost sector in red here. That's how we conceptualize it. Okay, so the actual area of this guy, if you want, let's call it A1. So A1 then would be, well, you know what? It'll be easy enough to put the whole thing in there. So why am I wasting time with that? I don't know. Probably because it gets late. And my brain doesn't work as well as it does during the day. Okay, so let's just get the whole thing at once. Let's remember to subtract off the area of the semicircle. So we're going to go to get the area of the cardioid below the x-axis. We're going to take the integral. I'll pull the 1/2 out front. I'll pull the 1/2 out front. And then what did we say angle A was? Angle B?
Shouldn't it be pi and 2 pi?
Pi to 2 pi. And then we have r squared. Okay, this is our R value for the cardioid. So 1 minus sine of theta, the whole thing squared, d theta, and we're not done. That just gets us the area of the cardioid below the x-axis. But any questions on that setup? Okay, what's the area of, well, let's start with a circle of radius 1. What's the area of a circle of radius 1? We know a formula for that, right? Pi times 1 squared, right?
Mm-hmm.
So what's the area of half that? Well, minus 1/2 pi. So if you actually take the time to evaluate that integral, I'll show you it does get kind of involved. let me back off the view a little bit. So here's the setup. And by the way, all of this is in the notes online, so you don't need to take a picture if you don't want to. So here's the setup. And then, of course, to evaluate it, I multiply this out, and you end up using that power reducing formula. And you can see it's a bit involved. It's not that much harder than the other one, but yeah, it's a bit longer. So I didn't want to take the time in class to do it. But that's what's involved in evaluating it. And it turns out to be pi force plus 2. So if you evaluate this, you get pi force plus 2 as your area. So it would be in square units. Another way you could think about it, if you wanted to make it a single integral, and it would actually have an advantage if you did it this way. If you set up this area as an integral, all it would be is, again, if you think about the circle in orange here, the bottom part of it is traced out with the same limits of integration. It's traced out as, and you could plot a few points to verify this, as pi goes from, as theta goes from 0 to 2 pi. So you could set up the area of the semicircle as the integral of, it would be 1/2 of, okay, it's still the same formula, r squared d theta, oh, r squared, okay, 1 squared, that doesn't do much. D theta, same limits of integration. And then what you could do is combine the two integrals, and when you square this out, you're going to have a 1 there, and you would end up, or 1/2 if you think of it as distributing the 1/2. And you would have a 1/2 or 1 here, depending on if you brought the 1/2 to the outside or how you think of it. And those ones would actually, since you're subtracting out this integral, those ones would actually cancel. So that would be another way to go. But I just mentioned it. I'm not going to do anything about it. Any questions on that? So the main thing here is, yeah, you should be able to evaluate integrals, but it's more important that you can, it really is more important that you can set them up. So really just, this is the most important part, setting it up. There we go. Any questions on that? Okay, I've got one more of these for you. Let me make the zoom factor, put the zoom factor back where it was. Okay. Example, find the area of the region common to the two regions bounded by the circle r equals -6 cosine theta and the cardioid r equals 2 minus 2 cosine theta. Okay, it's really important on one like this to draw a good picture. So I'm going to take some time here to explain that because I know a lot of you maybe need the review on polar coordinates. So let's do the circle first. Oh, so this is the circle we're talking about. And you really can verify that it's a circle if you just multiply both sides by r. Because if you do that, you'll get r squared equals -6r cosine theta. And then you can directly replace r squared with x squared plus y squared. And you can directly replace r cosine theta with x. And then to see what kind of circle it is, go ahead and complete the square on the powers of x. So bring the 6x over, make it x squared plus 6x plus y squared, and then you'll have 0 left on the right side. And then remember, to complete the square, you take half the coefficient of the x, write that down, and then you square it and add it. And then you got to remember to add it to the other side as well. So that this guy becomes x plus 3 quantity squared. So we get x plus 3 quantity squared plus y squared equals 9. Can you tell me then what the center and radius of that circle is?
-3, 0.
That's right. And then what's the radius?
3.
Yep. Okay, so the center of this circle is -3, 0. And the guy, when it's in standard form, like I wrote it, this guy is r squared on the other side. So it's the radius, just so you don't confuse it with like the r from the other equation. The radius is going to be of this circle is equal to the square root of that 9, which is 3. And so we're going to plot this circle at -3. There's the center, -3, 0. And then we're going to go up all directions, left, right, up, down, 3. So if I go left 3, 1, 2, 3, that puts me here. Right 3, it puts me at the origin or the pole. And then up 1, 2, 3, down 1, 2, 3. And you know, you're doing it freehand. It's not going to be the greatest circle in the world unless you're an artist. It's a little stretched out on the right side. That's okay. We'll survive. Okay. And yeah, your calculator will graph that in polar mode for you if you want to check it. But be able to put it, you know, convert to standard form. This is something any Calc 2 or especially Calc 3, which a lot of you guys are going to be, any Calc 3 student should be able to do that. Any Calc 2 student should be able to do that as well. Okay. Now this guy is a cardioid. Same reasoning as before. It's of the form a plus or minus r equals a plus or minus b cosine theta, and the absolute value of a divided by b is 2 over -2, and that's 1. So you know it's a cardioid. Cardioid, and it also tells you it's a cardioid. So let's go through and graph that thing. And you really do want to take the time to do this part, even by hand, even though you have a picture in your calculator. By plotting points, you can usually figure out what the limits of integration, or at least maybe one, in this case, one of the values of the limits of integration. Actually, I think we're going to have to plot the circle to figure that out, but we'll get there. You can often get the limits of integration doing it this way. I'll put it that way, but in this case, it might be a little bit more complicated. So once again, to plot the cardioid, just 0, pi halves, pi, 3 pi over 2, 2 pi. And then if I plug in 0, cosine of 0 is 1. So I'll get 2 minus 2, which is 0. We'll be at the pole. At pi over 2, I get cosine of 0, or cosine of pi over 2, rather, is 0. I'll get 2 then. At pi, I'll get 4. Does everybody see why? If I plug in pi for theta, I'll actually have a 2 plus 2 if I do that, because cosine of pi is -1. 2 minus 2 times -1 is going to be a 2 plus 2, 4. And then if I plug in 3 pi over 2, that's going to bring me back to 2. Plug in 2 pi, that'll bring me back to r equals 0. Okay, so, and keep in mind, because it's cosine here, I know it's symmetric to the x-axis. So when I draw this thing then, let me go ahead and plot the values. 0, 0. When I look straight up, I go out a distance of 2 like that. And then when I look in the direction of pi, I go out 4. 1, 2, 3, 4. 3. Look straight down. I'm going to have the point symmetric with that one. So look straight down. 3 pi over 2, you're out 2. And then you're back at the pole when you plug in 2 pi. So you're going to get a cardioid. Now, I didn't plot enough points to know exactly how wide it's going to get. But it's not going to matter as far as setting up the integral. So it's going to kind of look like a heart on its side. I didn't like the kind of the direction I started taking there. And then this bottom half should look pretty symmetric to the top half. Should be exactly symmetric, but I can't draw that well. Okay, that could have been better, but no, I gotta fix that. That's terrible, just terrible. Okay, if this is the point where it goes through up here, it better be the symmetric point down here. So put that in, gives you something to aim for. Bring it around there. That looks a little bit better. And it really is a cusp here, though. When this number is 1, you get a cusp. Okay. So to me, that's the hardest part, is trying to draw those things. Now, the next thing, once you have your picture in hand, you got to figure out what the heck region they're talking about, because that can be difficult. So let's read it again. Find the area of the region common to the two regions bounded by the circle and so the circle and the cardioid. Oh, so it's got to be the overlapping region. So you guys see what it is? It's got to be in here. I'm going to erase this in a second because it's going to get in the way, but it's got to be that region. Does everybody agree with that? So it's got to be the overlapping region created by those two boundary curves. Okay, so if you're all okay with that, then here's where the representative polar sector is going to come in handy. So look, remember, I'm going to draw an analogy here because I think it'll help. If you thought of like in the XY plane, so here's X, here's Y, and you had two curves like stuck together. You had a curve here and then maybe a curve like this, and they're given by different equations. Like this is y equals f of x in blue, and then y equals, well, the curve's in blue anyway, and y equals g of x, right? And let's say you wanted to find the entire area between the x-axis and those two curves. Then it's not what we would call vertically simple, because if you draw a representative rectangle here, the top of it, the roof of the house is going to be different than if you draw the representative rectangle over here. So if you actually wanted to set this up, finding the integral, you'd have to set up two separate integrals, and you'd split it up where it changes, the roof changes from f of x to g of x. So if this were a c value and this were an a value and this were a b value of all a, b, and c values of x, then you'd have one integral from a to c of f of x to represent the area, and then another integral from c to b of g of x to represent the area, and then you'd add them together. And the reason I mention that is because it puts you in familiar territory. Any questions on that? Because something very similar is about to happen here in polar land, except it's going to be with the polar sectors that I draw and not vertical rectangles. It's going to be with the representative sectors or sector, not with a representative vertical rectangle. So I guess we would say this. Let's go back to the region now and finish the analogy. The R value is not radially simple. So let me zoom in and show you. It's critical to understanding this problem that you follow along with me right here. So let me zoom in on this picture. So remember the region we're trying to find, it's this entire region, right? However, once you cross, okay, so imagine you're either tracing out the cardioid or the circle, it doesn't matter. Once you cross the intersection point, then the way you draw your representative polar sector would change. So in fact, let me draw on kind of a line here that goes right to that point. So if I draw on that line, and pretend like I'm hitting the origin right there. If you drew in your representative polar sector angle-wise before you get to that line, your R function would be given by the circle. And that I'm just drawing in a radius there instead of making it look like a sector. But there now it kind of looks like a sector. The function you would hit over here is the circle in green. But if you drew your representative polar sector beyond this black line that goes right to that point of intersection, if you drew it, let me use a different color, blue. If you drew it over here, then to stay in your region, the function that you would hit would be the cardioid. So, like the circle's like the f of x from the Cartesian example a second ago. And the cardioid's like the g of x. This is not radially simple, in other words, this region. So if we want to find, the area of this entire polar region, then we're going to have to take that into account and create two different integrals. Does that explanation kind of make sense? You may not understand how to create the two integrals yet, but does that help? Okay, so
Professor, I just have a quick question on where exactly did you know that, or how did you know that that was going to be the intersection point?
Well, it's a boundary. Well, how did I know? Well, I haven't found the intersection
-3.
point yet, but I could tell from the two pictures that I drew that it would have one.
Okay, I just wanted to.
Yeah. No, but you bring up a good point. We're going to have to find at least the theta value of that intersection point, because that's where the function that we use, that we throw into the integral, is going to change. It's going to be the circle before you get to it, and it's going to be the cardioid after you get to that point of intersection. Okay, now, before we go any further, though, I have to convince you of something. Well, okay, let's go ahead and find the intersection point since we mentioned it. It really doesn't matter if the order in which you do some of these things anyway. So let me make some room here. Okay, and let me move this guy over here. Okay, so to find the intersection point, we're going to need that to set up our limits of integration. Well, okay, at the intersection point, the R values will be the same. The R values will be the same at that intersection point. So what you can do is you can set the right-hand sides, they're both equal to R, set the right-hand sides equal to each other. And if you do that, you'll get -6 cosine theta is equal to 2 minus 2 cosine theta. Now I'm gonna add 2 cosine theta to both sides, which gives me -4 cosine theta equals 2. And then if I solve for cosine and reduce, I'll get -1/2. Does everybody see that? -1/2. And then if I solve that trig equation, I'll actually get two values. 2 pi thirds. That would be the value in the second quadrant. And then also 4 pi thirds, but that would be for the theta value of that bottom intersection point. So if you have questions on how to do the trig on that, I'm happy to answer it, but I'll have to do it after class, because if I do it now, we're going to run out of time. So my claim then is for that upper point, this guy right here, I don't know what the R value is, and I don't care. The theta value of that point right there is going to be 2 pi thirds. And so my plan then, because we have a lot of symmetry going on here, my plan is to just find the area of the region above the x-axis, and then I'll double it. So I don't even have to mess with this intersection point down there, okay? Now, if you draw in, once again, that representative sector, remember, before you get to the intersection point, the R that we have to plug in is the circle. So to start setting up this integral, so our area is going to be, first of all, I have to remember to double the area because I'm only setting up the area for half of the region. So I'm going to double it right away. Put that 2 on the outside of some brackets. I'm going to use my formula, 1/2 a to b r squared d theta. And I'm going to have to use two integrals here. So for the first integral, 1/2, I don't know what the starting a is yet. That's not obvious here. But the b value, remember, these are angle values. That's going to be the 2π3. That's where we're going to stop it at. And then I'll figure out the lower limit. I'll show you how to figure that out in just a second. But remember, the r value, before we get to this intersection point, the r value is going to be the circle. So it's got to be -6 cosine theta, square the whole thing. D theta. And then, like I say, I'll get this lower limit in a second, but just so you don't forget what we're doing, then we're going to have to add that to another integral where the r value, if you look at this representative sector, the r value of that is going to be given by the cardioid. So you're going to have to, for your integrand, you're going to, for your r squared, and we'll put the 1/2 on the outside, you're going to have to take the 2 minus 2 cosine theta and have that as your r. So that's your r squared d theta there. And then all that's left to do for the setup anyway is to find all the rest of the limits of integration. So before I go about showing you how to do that, any questions on the rest of it? So we almost have it now. Okay.
The
Yeah.
limit.
Go
on
ahead,
this?
Nancy.
What goes on? You've got 2π/3 at the top of at the front.
That's the theta value that would produce this intersection point. Yeah.
What goes on the bottom?
What? No,
What
no,
he's
no.
talking about the upper limit and
No,
of
no, the
that,
2π/3 would actually be the upper limit.
Yeah, so what's the lower limit?
Oh, that's what we're about to talk about. So we're not finished by any means, but I wanted to ask you if you had any questions on what I've done so far. Okay, then to get the lower limit of integration, that's what I want to talk about next. So let's go back to our picture here. I have to convince you, oh gosh, it's kind of a mess now. So what I'm going to do is take this picture and go to a nice clean spot to convince you of something. Okay, so remember the equation of that circle is -6 cosine theta. So just focus on the curve in green. The equation of the curve in green is -6 cosine theta. Now, if you were going to trace that out by hand and not convert it to rectangular coordinates, then much like plotting the cardioid, this is what you'd get. You get a table, r and theta. You'd maybe start at theta equals 0. Now, if you plug 0 in there, you don't get 0 popping out. Cosine of 0 is 1 times -6 is -6. Oh, look. When you plug in 0, theta equals 0, you get this point, which isn't anywhere near where we want it. So, oh, okay. So what happens when you plug in π/2? That would be the next one I usually plug in. Oh, if you plug in π/2, cosine of π/2 is 0 times -6 is 0. So this thing, the bottom part of this circle is traced out as theta goes from 0 to π/2. And you end up right here. And then we already know that the theta value of that point is 2π3. So as you go to 2π3, this part of the circle must be traced out. Let me use a highlighter. Or just a bigger blue curve. Oh, wait, I'll do a yellow curve. Okay, so as you go from π/2 to 2π on the circle, it's got to be this part, 2π3, that is, this part of the curve that's carved out. That's what we want. That's the arc that we want on that circle. So the limits of integration must go from pi halves as the lower limit to 2 pi thirds. I know that's not easy when you're still getting used to polar coordinates. I know, but that's a good way to do it. Graph the darn thing by hand. I mean, get the graph on the calculator first so you don't make a mistake, but graph the thing by hand and verify that you're looking at the right length of arc so that you could set up your limits of integration between the two endpoints, the theta value that gives the two endpoints of that length of arc. So long story short, this bottom value here turns out to be pi halves. So that gets us to this point. And then over at this integral, once you get past theta equals 2 pi thirds, then the r value changes to the cardioid, and we're over at this integral. So, when does it change? Across 2 pi thirds. So that's your bottom limit over here. And then your top limit, hopefully it's clear, your top limit is going to be, we're going to go all the way to here, which is on the cardioid, which is pi. So 2 pi thirds to pi. And then that gets us half of the overlapping area if we add those two integrals together, and then outside the brackets double it, you get your whole area. So let me back off so we can see all this. So yeah, it's all there. That's now you can distribute the two and get rid of both 1/2, and it looks a little nicer, but that's the setup. Any questions on that? I'm sure you probably have a lot of questions. That one is if you can understand that one, or at least mostly understand it, you're in great shape. That's the hardest one you'll see. At least I think. I can't guarantee that. Surprisingly enough, when you evaluate the integrals, you get nice values for these polar integrals. It's 5 pi. 5 pi square units if you evaluate that thing. Any questions? So I'm going to leave it there as the setup. But if you were going to evaluate this, you'd distribute the two, get rid of the 1/2, and evaluate those integrals. I know. Don't go ahead.
Yeah, I got just kind of a basic question. You mentioned that the little slice that we're putting through here to measure the area. In the other examples for grabbing area, you said we were using like really, really small rectangles, and you made a similar analogy to this one. But did you say it's really a rectangle, or is it more like a really small sliver of like a triangle?
Okay, wait, back up. For Cartesian regions, we used rectangles.
Right.
For these regions, we really think of them as polar sectors.
So like
so a sector is not quite a triangle. They're almost polar sectors. A sector would be like a slice of pie, and really the area is what we're concerned with.
Okay.
So it's not a triangle because the crust of the pie is an arc on a circle.
Oh, it has an arc. Okay.
Yeah, and normally the little lines I have here, those would represent almost sectors. Because, the curves themselves aren't usually circles.
Okay, cool. Thank you.
But in the infinitesimal, they're close enough to circles. Okay, so that was shocking, I know. But just, get as good as you can at this stuff. I don't expect you to be great at one like this, but certainly one of the other two problems should be doable on a test, I think. This one, practice it. See if you can get to where you can set this one up. And you'll do more in Calc 3. It actually gets a little easier in Calc 3 when you talk about double integrals. Conceptually, it gets a little easier. Okay, last thing. So if you want to find the arc length of a polar curve, you can do it. And you could use the same formula since for any polar curve, we can parameterize it. X equals r cosine theta, y equals r sine theta, and then you fill in whatever r you're given in terms of theta. You fill that in for r, and you've got yourself parametric equations. So you can use that same formula to find arc length. S equals integral a to b, if theta goes from a to b, square root of, instead of dx dt squared, it would be dx d theta squared. because theta is the parameter. But other than that, you know, it really is the same formula. And then dy d theta squared. And then instead of dt, d theta. Now, that's not the formula I'm going to present to you, because if you actually generically take these derivatives, you actually have to use implicit differentiation. But if you do that, and then you use that trig identity, cosine squared theta plus sine squared theta equals 1. If you use that actually a couple of times, I derived it earlier to see if I had time to do it in class, and I don't, but it would be a cool derivation to use. But you get a simpler formula to use if you do that, and here it is. So you get S is equal to the integral from A to B, same thing so far, square root of, it turns out to be r squared plus dr d theta squared underneath. And then d theta on the end. So in other words, this guy simplifies to be this guy. And this guy is an easier formula to use for polar curves. So that's the one we're going to use. So let me show you just one more example. I know it was a lot tonight, and then that'll be it. And we'll use this formula. So let's find the arc length from theta equals 0 to theta equals 2 pi of the cardioid given by, I think this might have been the one and then the last one, wasn't it? 2 minus, is that the same one? Yeah, same one. So same picture. So we won't spend a lot of time graphing it. In fact, I don't think we'll graph it at all. So if you think about it, that cardioid, the entire cardioid is traced out from 0 to 2 pi. So we're finding the distance all the way around the cardioid in this one. So, you know, write down the formula. And I'll say this again. While obviously I can't force you to memorize these when you're at home, and in fact, you know, I gave up on that because I didn't want to punish the honest students. We have a lot of honest students in this class who, if I told them, hey, don't have anything written down, they wouldn't do it. But then I know that there's always a handful who would have it written down, and that's not fair to the honest students, which is most people. So I wanted to be fair to most of you, and I'm going to let you have those two cheat sheets on the final again. They're not cheat sheets, but that's what I like to call them. And so you can have this written down, but be familiar with it. If you're not familiar with the formula, it doesn't matter if you have it written down. You probably won't be able to figure it out how to use it on time if you haven't practiced it in the middle of a test. So, so write it down. So it's the integral a to b. Remember, it's r squared square root plus dr d theta squared. And then d theta up there. So we're using the second formula I presented to you, that one. Oops, too far. Okay. So let the formula tell you what to do. Guys, you have to memorize a lot in math. And I don't like it any more than you do. But don't memorize more than you have to. If you let the formula tell you the steps, you don't have to memorize the steps. So since you have to, in most classes, memorize the formula anyway, memorize or write down the formula in this class and let it tell you what to do. And you don't have to write down the steps then. So what is this? Look inside the square root. What does it tell me to find?
The derivative.
The derivative. So what is dr d theta? Mate. Dr d theta. That's how a pirate would say it. Dr d theta mate. If they knew about derivatives, I don't think they did. So what's dr d theta, you guys? Oh, what's r? Well, it's this guy. So what's dr d theta?
2 sine theta.
2 sine of theta. There you go. All right, because derivative of cosine is negative sine. Oh, there's already negative there. Okay, so set it up. S is going to be the integral from, oh, what's A, what's B? 0 to 2 pi. Okay, and then square root of R squared. Oh, well, we can't put in R. It's an integral with respect to theta. We have to put in R in terms of theta, you guys. So 2 minus 2 cosine theta, the whole thing squared. Extend that, and then plus 2 sine of theta, the whole thing squared. That's dr d theta squared. And then d theta. Any questions on the setup? I don't know if I have time to do the whole thing, but I do want to show you a couple of tricks with this one. Okay, so in order to evaluate this integral, what do we have to do? Take a guess. I'll bet you'll be right.
Identity.
Oh, yeah, that's a good guess. You're using your crystal ball. You're looking ahead, yeah. But before we apply that, what can we maybe do with the 2 minus 2 cosine theta?
Factor out.
Pull out a 2.
Okay, how about we just multiply the whole darn thing out, though?
Yeah.
Yeah, okay, so it's going to be the square root, and you could do this separately if you didn't want to carry all the integral symbolism around with it. You could do this as kind of scratch work. So if you multiply this out, think about it, you square the 2, you take minus, so we're multiplying out like a binomial-like quantity, so 2a squared minus 2ab plus b squared. So square the 2, multiply, subtract off, multiply 2 times 2 cosine and double it. So what does that make, 8 cosine? And then plus the last guy squared, which would be 4 cosine squared theta. So that's just that guy. And then don't forget to square the 2 on the 2 sine of theta, the whole thing squared. So 4 sine squared theta. And then d theta outside the square root. And then this at least gives me an opportunity to show you that trick, which comes up a lot in polar integrals, where we're going to use a well-known identity. So if you think about it, you have 4 cosine squared theta here plus 4 sine squared theta. If you factor out the 4, don't you have inside the parentheses cosine squared plus sine squared theta left? And what is that?
1.
1.
That is 1. Okay, so that, 1 times 4 is 4, plus that 4 gives me 8 right there. 8 minus 8 cosine theta underneath the radical. And then, so we get that. And d theta. And then I'm going to factor out 8, you guys. But then that means I can pull out a square root of 8. I can split up the radical over multiplication. And let me shrink this down a little bit. So underneath the radical, I can pull out an 8 and get 1 minus cosine theta left. But then that's underneath the radical, 8 times 1 minus cosine. I can make it 2 separate radicals, square root of 8, but that's 2 rad 2. So I'm going to pull that out front. That's square root of 8 out front, 0 to 2 pi, and that leaves me with just 1 minus cosine theta, d theta. And then another really cool trick when you have like 1 minus cosine theta or 1 plus cosine theta underneath the square root. I don't know if we've seen this trick this semester, but you can once again use the power reducing formula, but in reverse, raising the power formula, I guess you'd call it. So if you think about it, okay, let's write down that formula again that I wrote down earlier. In terms of, well, actually, I think we're going to have to use sine here. In terms of sine squared theta, what does that reduce to? 1, not plus cosine, but 1 minus cosine of 2 theta all over 2. Oh, but we don't have 1 minus cosine 2 theta, so let's make it 1, let's make it half that. So the angle is theta there, and then we've got to make it half of what it was over here to make that make sense. Does that make sense? So look, if I could just somehow put this guy over 2, I'd have that, and then I could replace what's underneath the square root with this guy, and then I could actually take the square root of the squared quantity. So it's a really slick trick. I don't know if we've seen it this semester, but the idea is this. I want that division by 2 there so I can use this identity. I'm just gonna put it in there. Oh, and then I have to compensate by multiplying by 2, but again, since the operation's multiplication here, I can pull out another square root of 2. I can break up the radical again. And then that leaves me with, okay, so I'll put the radical 2 that I'm factoring out here, I'll put it right there. That's gonna be 2 times 2 or 4 out front in the next step. And then I can replace, oops, I went down too far. Look, I can replace then, so that's supposed to be 0, and then I can replace this guy, that's what's left underneath the radical, with this guy. Sine squared, I'll call it theta over 2. D theta. And then, so this is 4 out front. Oh, I did have the 0 there. I just wrote it too far down. And then integral 0 to 2 pi. And then we'll have sine of theta over 2 d theta, which is easy enough to evaluate because I'm out of time. You'll end up getting a really nice number, 16, if you evaluate that integral. So I showed you the 2 tricks I wanted to show you, using the power reducing identity in reverse, and then also using the cosine squared plus sine squared theta identity. I didn't quite get to finish the integral, but that's okay. Any questions on that? I can almost fit it on one screen. So yeah, I know it's symbolically intensive tonight, I know. But now you have the weekend to study, spend several hours on it. I know, don't blame me, I didn't invent this stuff, but it takes several hours of study to really get this stuff. The good news is it's a good review for some of the stuff we did in chapter 7 with evaluating integrals.